Oh, darn it. Did you have to go chase a calf?
No, I just lost my internet connection for no good reason.
Oh.
And I'm so disappointed that So what are you making, Hannah?
This is not coconut milk. Look at it.
Ew. Is that like coconut oil?
Is it cold? How cold is it?
It was room temperature.
We would think it
Not
should be
cold.
colder than that.
Should I not use this one? I'm making a pina colada smoothie, but
Well, as long as it was sealed, it should be all right. Now, what are you going to make? This cooking hour?
I make my smoothie too. Hannah got me in the mood for a smoothie.
I see. Well, it's going to be a little difficult with what we want to do here to be distracted like that. I'm sure you'll figure out a way. So
I opened the pan on the wrong end.
Whenever you get done with your cooking, in the APBio folder, I put a sheet which you do not have to open right now. You can look at the screen, but we have the general class info. And in the general class info folder, there's a document, AP Biology Equations and Formulas for 2020. And it looks like this.
Oh, I have that in
Yes,
paper.
you should have that. I think I gave it to you and it's easily accessible. I think I gave it to you way long ago. And it's easily accessible online. And it's in about any document you want to talk about. And we need to look at some of these things, except I probably need it in a different browser so that I can do my pen business.
Okay.
So how am I going to do this? Let's see, different browser. Plan B. All right. So it got all quiet all of a sudden. I assumed you guys muted yourself so you could talk to your parents in the kitchen and still be all right. We wouldn't have to listen to the the blender going woo. So I want to talk first of all about the concepts, the first three concepts in this first box. Recently, when I've switched to the pen in this app, the app is locked up, so we'll see how this goes. Does not want to let me use the pen. Well, this is not working as smoothly as I had hoped it might. So let me try one more thing. All right, let's see if this one will let me do it. Okay, this won't let me use the pen function either. So we're just going to have to get creative.
Try downloading it as a document, not as a PDF.
Well, what I thought I would do was Shift Windows S and then take a picture of this piece of the screen. And then, oh, let's see, probably paste it into Word. And then use the Word pen. So I think this will work. All right, so mean, not Michelle or Mrs. to you, not cranky or me to you. But you know that mean is average, and here's the complicated formula for it. And you're probably good with the idea of finding the average. Basically, add up all of the numbers and divide by the numbers that are there. That's the general formula for it. What we need to talk about some is standard deviation and standard error. Now, you will notice this little asterisk for standard deviation and then again for standard error of the mean. And if we look at underneath these boxes here, it says, for the purpose of the AP exam, students will not be required to perform calculations using these equations. So you're not going to be have to be able to do standard deviation. You're not going to have to do standard mean, but you do need to know what they mean and how they're used, because that's what it says next. However, they must understand the underlying concepts and applications. So we will actually do some really, really simple ones just to give you an idea of what they're supposed to do. Okay, so standard deviation over here on the right, except I got part of your picture in the way from where I copied the screen. Over on the right, it tells you what everything means. So X bar is the sample mean, or the average of the group of numbers we're talking about.
Are we supposed to see your word, or are we supposed to see your drive? Because right now all we see is the drive, not word.
All right, thank you for telling me that. I need to share it differently than I had been. I just want to generically share the screen. Now, all right, now you seeing the word?
Yep.
Thanks for pointing that out. So standard deviation, there's the asterisk, and standard error of the mean, there's an asterisk, and the asterisk says you don't need to know how to do them, but you do need to know what they mean, how they work. So again, mean is average, standard deviation, X bar is the sample mean. So if I had 5 numbers, 6, 8, 10, 11, 12. So that would be 33, 39, 47 divided by 5. Oh, I don't know.
9.1.
All right, so that would give us a average, a mean of 9.1. So given these 5 numbers, the sample mean would be 9.1. Well, the sample size is how many we had, which was this 5 right here. So the sample size is 5. So what they don't list here for you is xi. So this would be x1, this would be x2, this would be x3, this would be x4, this would be x5, and the I means we're adding up x1, sum of. See, sigma is the sum of all of them. So we're going to add up each of these subtracted by 9.1 and then divide it by n minus 1 or 5 minus 1. Now, I probably didn't say that clearly enough. I don't know how to say it clearly enough. People kind of have to do it a few times to start to get it. It was kind of like when we did chi-square, which we'll do some more of, where we had to do the same process for every number we had. So what this ends up being, what this line right here ends up being is x1. So 6 minus our mean, 9.1 squared. Sum is plus, so plus x2 would be 8 minus 9.1 squared. Now, this is really a simple process if you can understand what the equation means. If you have a huge amount of data and you're doing it by hand, then it's not difficult. No, a huge amount of data and you're doing by hand, it's not hard, but it's very tedious and time consuming and easy to make mistakes. This is a great thing to use a spreadsheet on and learn how to write it. In fact, most spreadsheets have standard deviation functions. So all you have to do is enter in the numbers and write a simple calculation, which we're not going to do right now anyway. So x3 would be the third number, 10 minus the average, 9.1 squared. And then the fourth number would be 11 minus 9.1 squared plus 12 minus 9.1 squared. And basically, we just took this number, stuck it in there, this number, stuck it there. I'd have too much clutter if I keep doing that. You get the trend, I hope. If you have questions, ask. So we do all this. And if, Josh, do you have a calculator there? Does anyone have a calculator handy?
$9.4, but
All right, you calculated it, you got 9.4.
for the actual average.
Oh, the actual average is okay, so 9.4 for each of these.
Yeah, I guesstimated before.
That's fine. I was going to do that. All right, so to give you an idea how these work, if Josh is working on it and gets it done, I don't want to have to take time to go all the way through it, but to give you an idea how it works, you would put it in your calculator, 6, need parentheses, so it does the squaring right, parentheses, 6 minus 9.1, close parentheses, squared, plus open parentheses, 8 minus 9.4, close parentheses, squared. And Josh, if you get a number, you can just shout it out and cut me off. Then the third one, 10 minus 9.4, close parentheses, squared, plus 11, open parentheses.
23.2.
23.2?
Yeah.
Okay, so that would be our top, 23.2. When we did all of this, which we did up here, then we got 23.2. That's again, it's not hard, it's just annoyingly time consuming. So n was our sample size. We had 5 x's, 5 numbers. So it's 23.2 divided by 5 minus 1. Or divided by 4. So
That's 5.8.
all right, so that means that our standard deviation for these numbers, well, first of all, our mean, which is x bar equals 9.4, and our standard deviation equals, what'd you say, 5.4?
Yeah, I had 5.8, and then I took the square root of it because that's what it tells, because that's what the formula thing says, and I got 2.41.
Okay, yes, so we have this square root of the whole thing, that is correct. And 2.4?
Yeah.
All right, so mean 9.4, standard deviation 2.4. The fact that they both end with 0.4 is irrelevant. It just happened to luck out this way. There's no rule or no indication that they have to do that. So you're not going to have to do these on an actual test, but you do have to have some idea of where it comes from, and therefore some idea of what it means. Now, standard deviation. We did this complicated formula, and what did we come up with? Now, this is what I'm about to tell you is oversimplified, maybe to the point of being technically incorrect, but it works for a vague understanding of the process. It actually works for more than a vague understanding of the process. This is the average number away from average. And I see that I have to run out for about 3 minutes. Somebody's here and I have to go have a brief word with them. So go ahead and make your...
Oh, so good. But
Why did we
All right,
like
so I'm back, sorry. Sounds like you were having loads of fun.
you need to put this, just this clip on YouTube.
Well, I didn't record it.
It's recording.
recording?
I just restarted the recording.
Aw.
So standard deviation is basically the average away from average. Now, that's a little bit oversimplified, but it gives you a good idea of what the concept is talking about. So let's say our 5 numbers, instead of 6, 8, 10, 11, 12, had been 6, 8, 9, 7, 8. Now they would have been a lot closer. We would have got a smaller standard deviation. So basically, the bigger this number is, the more spread out your data is. And so if it weren't for this -1 right here, it would be the average away from average, but it's almost the average away from average. In fact, 9.4 is our average. 9.4 is not on the list. It would be right here. So actually no number was average in our original list. The standard deviation tells us on average how far a number was away from average. Now, why would we care about that? Well, if you remember from psychology, that bell-shaped curve, average is here, and it turns out that plus or minus 1 standard deviation almost always contains, I forget the number, 80%, I think, of variation. And then plus 2 standard deviations, almost, plus and minus 2, almost always contain a certain amount. So that bell curve is based on the standard deviation. And listen, the bell curve or the natural curve happens. We don't make it happen. We have seen that it does happen. It's the way things distribute in nature. Can't really explain why, but it's what it does. So standard deviation is basically the average away from average. And it's time consuming, but it's not necessarily. I'm getting some weird feedback. I'm muting you folks. If you want to say anything, you can unmute yourself. It's an important statistical tool. Things fit. Why do they fit? That's the way God made it, I guess. That's statistically how things work out. I don't know, but they do. Now, standard error. Standard error is something that you are probably more likely to need. Whoops, that's not what I wanted. Standard error is probably something that you're more likely to need for the test. Standard error, once you get standard deviation, standard error is incredibly simple. Standard error is S, which comes from here, divided by the square root of n, which comes from here, or is the sample size. So standard error in our example would be 2.4 divided by the square root of 5. Again, if you don't see where I'm pulling this stuff from, by all means ask. What's
1.07.
1.07, so we'll call it 1.1. So the standard error in this case would be 1.1. Now, what in the world does this tell us? This tells us, if you see a graph, whoops, and they have, let's say, a bar graph, and they've got their standard error lines like this. Now, they're going to tell you someplace in the key, standard error equals 1 or standard error equals 2. So big mistake people make with these graphs is they just look at the bar. But they're sampling error and all kinds of things. So the bar isn't necessarily accurate. So what they're telling you with standard error is that it's the top of the bar within this range actually. So it could actually be anywhere in this range if they say standard error is 1. If they say standard error is 2, then they would have bigger bars, and they would mean that it could be anywhere in this range. So why does that mean anything? Let me get myself some clean space here. Should be some down here. Let's say that we have a bar graph, and we've got 2 sets of conditions. Now, if I look at these 2 sets of conditions, is there a difference between the 2 columns in the bar graph? And I think that the obvious answer should be yes, there is. There certainly is a difference. But sorry, my screen's, I'm losing track of what I'm doing here. But when we had error bars, is there a difference between those two graphs, those two bars on the graph? So if the left bar could be in this range and the right bar could be in this range.
So they have like a overlapping part, but they're different. Like,
Well, if you
Yeah.
just look at this part, it looks like they're different. But if you look at the standard error, it's telling you how far off they could be. So let's try looking at it this way. 8 plus or minus 2. 9 plus or minus 2. Careful. Are those different numbers? Are those different values? 8 plus or minus 2, 9 plus or minus 2. 8
The
to 10 to 6, 9 to 11 to 7. If this can be anywhere in this range, and the 8 plus or minus 2 can be anywhere, I'll use different color, anywhere in this range, can I actually trust the fact that I got two different numbers? I mean, obviously 8 and 9 are different numbers, but can I trust that difference when I've got this much overlap between the ranges?
It depends on the thing, I'm guessing. Whatever
Well,
you're measuring.
at this point, I cannot trust those two numbers if they have that much overlap. Is there a difference between 8 and 9? Not when they have this much overlap in their possible error. This is what standard error is trying to tell us. So it's very, very important when you have to analyze a graph that you not just look at and by the way, they're not just used on bar graphs. So let's say that I have a line graph and I've got these points. And each point should have the same standard error. Come on, I'm picking my pen up for some reason. So I've got that line on the graph, and then I've got this line on the graph. Now, if I look at these lines, just the lines, I say, well, they're obviously different. But actually, this should not be viewed as a line. It should be viewed as maybe this will help you. It should be viewed as a swath. So this should be viewed as a swath that goes, my hand isn't sliding on my pad very well. Keeps picking the pen up. So this should be viewed as a swath that goes between the error bars like this. And then the same thing for the blue one. The blue, I don't know how this is going to show up. I don't know how these colors are going to work together. The blue one is a swath that goes between the blue error bars. It works pretty well, actually, except for when it jumped off. Sorry. But see this dark green area in the center? That dark green area in the center meant that we can't trust our data enough to say it's different. The range of possible answers that we could have gotten legitimately for the blue and the range of potential answers that we could have legitimately got for the light green is so broad that they overlap each other, and we cannot actually say that they are for sure different, significantly different, that there's actually a difference between those two. I don't know, does this make sense? Am I just talking?
Well, the thing is like I almost feel like that this would, maybe I haven't been listening well enough, but I would still feel like this is still a difference depending on what you're looking at. If you're looking at
Well,
material, like for example, here, just thinking off the top of my head, if we're talking about you have enough material to make 8 to 10 nuclear bombs versus not 7 to 11 nuclear bombs, I feel like that would be a significant difference.
well, yeah, okay. I would grant you that, but we're talking about measurements we've taken from the real world. So you should view it as, well, I went out and I measured how tall this tree was and I got 100 feet, but it actually could be, actually, there's a better way to say this. 10 people went out and measured a tree, and 10 people got slightly different answers: 101 feet, 99 feet, 102, 98.7. And which of those is exactly the right answer? And the thing is, we don't know which is exactly the right answer. Maybe we get a better measuring device, and later we can figure it out. But we have error in our measurements. Always there is error in measurements. We want the error to be as small as possible, and the smaller the error, the smaller our error bars would be. So if we were approaching perfect data, we'd have, you know, error bars that were just barely off the dot. So error bars like this signify almost no offness in our measurement. Error bars like this signify a lot of offness, variability in our measurements. And as long as there are variability in the measurements, we cannot be sure if the possible range of variability overlaps each other. And by the way, when I say significant difference in science, significant is a definition. It isn't how we necessarily use the word significant to mean important to us, or it seems like it could be a big deal. It is actually has to meet a certain set of criteria. And that's where like the chi-square law that we did the other day came in. And so we're going to be doing some more chi-square. But significant is defined in science. It's not, seems like to me or you or anybody else. And by the way, that's where a lot of the arguments about this COVID business are coming. The scientists are saying, statistically, it does not meet the criteria of significant, like for the number of people who improve with a certain treatment. And the average guy on the street is saying, well, it looks like it was an important difference to me. So yeah, there's a difference between significant and significant, depending on who's talking about it even. But the definition of significant is, when you come to a graph, if the error bars overlap or two sets of data, then we cannot, okay, let me say it's slightly different. If the error bars overlap for a set of data, these 2 points might actually be a real difference, but because the error overlaps, we cannot know that it is a significant difference. All right. Any questions? I don't know if any of you read my information email or not, because it always says AP Biology every day. So just in case you, and that's fine, but just in case you didn't read it, on Thursday, Mr. Pahalski is planning on doing something at in this time slot, some kind of a Zoom or some other platform meeting during this time slot. So we will not, unless he changes his mind and cancels that, we will not be meeting on Thursday. But otherwise, tomorrow we are going to look at some more graphs with some error bars and try to make sense of what they mean and if they're any good. So do you have any questions?
Nope.
All right, then. You guys have a good day. It's nice outside if you get a chance to go out. And we'll talk to you tomorrow.